Okay, Assalamu alaikum. Am I audible?
Yeah.
Okay. Okay, so in the last class we discussed till this point as far as I remember. Now, today we will continue with standard enthalpy of formation. Okay, so I have sent some questions, right? So you can try them. Before we study this standard enthalpy of formation, let's go back and try some questions, right? Here, okay. Can you just try to answer the 27th question? We have already studied about the
Which one?
activation.
27th one?
Yes, I'm sorry. Yeah, 27th one, this one.
No, it's okay, continue, sorry. Oh. Okay. Oh, I'm not sure.
Okay. So now we have just studied the activation
I haven't.
energy. Yeah. Can you hear me now?
Yeah.
Okay. So we have just studied activation energy. So if you read the question, activation energy of the elementary reaction, right? So elementary reaction means this is a reaction happening in one way. Okay. So one step. So
Okay.
okay, so this reaction is catalyzed, right? So we are using a catalyst here. So what is the function of catalyst? A catalyst,
To provide an alternate reaction
yes,
path
alternative
less
reaction
activation
path
energy.
where activation energy is reduced, right? Activation energy is reduced
Yeah.
by the metal M, right? So here as the catalyst we are
Yeah.
using metal M, right? The energy diagram of the catalyst reaction is given below. Now we have been given the energy diagram after the catalyst was administered to the reaction system, right? So it should have like this, right? So previously before we added the catalyst, this might have like this, the activation energy might have like this. Now it has provided an alternative way where the activation energy, right? So this is the activation energy, so this should be the activation energy before adding the catalyst. Now which of the following is always correct with regard to this reaction? Okay, so now you see from A to B, right? So there is an intermediate. Can you see this intermediate? This intermediate.
Yeah.
Again from this intermediate another intermediate is coming. From that the C, the product is produced, right? So here this
Yeah.
reaction is happening in how many steps?
Mm.
One step, then two step, then three steps, right? Do you understand?
Yeah.
From, let's say
Yeah.
this is, okay, let me erase all of these. Okay, now let's assume, let's say this is X, right? X, and this is
Yeah.
Y. Okay, so from
Okay.
A plus B gives you X, then X becomes Y, then from Y we get C, right? So this is the first step reaction, this is the second step reaction, this is the third step reaction. Now if you add these three reactions, you will get the overall reaction where this X and this Y will go, and ultimately you will get A plus B becomes C. Okay. Now to produce X from A plus B, we have this amount of activation energy, and during that reaction delta H1 amount of energy is absorbed or released.
Is absorbed.
Absorbed. Then from X to Y we have E2. What is the okay for the step 2 reaction from X to Y? What is the activation energy?
E2.
You see, from this it should come E2, right? And this is let's say if this is delta H2, then E2. E2 plus delta H2 is the activation energy for the second reaction. Okay. Then E3 is the activation energy for the third reaction. Now you see it has given an alternative pathway. Now let's say if this is an elementary reaction, elementary reaction means there should be only one step, there is no intermediate. It should have happened like this. From A plus B to C should have come directly without these steps, right? Now let's say for this reaction, that is EA. Okay, now let's assume that is EA. Now you see EA is this. Now it has reduced EA to this point. If you add catalyst, EA has reduced. Now what relationship can you tell about this? Now can you just look at the picture and pick the answer?
Okay, so EA is E1 plus E2, no, E1 plus E2 plus E3. EA is, it's 1 plus E2, 5, I think.
5?
I think.
Is this the answer?
I believe so, if I'm not sure.
Okay, so now we will check. Now you see this is the highest activation energy point after catalyst was administered, right? But before that it should have like this. It should have beyond this E1 plus E2, right? So now you see this is the new activation energy EA1. Let's say EA. Okay, now that is the activation energy after the catalyst was administered to the reaction system. Now you see this is let me erase all this. Okay, so now you see it should be like this. Okay, this is the EA, this is EA. Now just by looking at the picture you can tell EA should be anyhow greater than this point, right? So this point is what? From here to here, that is delta H1 plus E2. Okay, delta H1 plus E2. So the initial activation energy should have been greater than this E2. So EA should have been greater than delta H1 plus E2. So this is the correct answer. Did you understand this question?
Yeah.
Okay. So elementary reaction means it should have happened in one direction. But after we put the catalyst, it is happening in 3 steps. So it has given an alternative pathway to the reaction, right? So now this is the relationship. So from this what you can tell, an elementary reaction also can be made to many step reaction if you insert catalyst. Okay, so elementary reaction means a reaction happening in one step, but after catalyst was administered, here you can see 3 steps, right? So this is the alternative pathway. Okay. and again there was a question in galvanic cell. Okay, wait. Okay, anyhow, we will just discuss these things and then come to the questions later. Okay, now we will focus on standard enthalpy of formation, right? So now we are studying energetics, right? Energetics. Now we have some definitions in energetics, right? Definitions in energetics. Now we are going to be studying about enthalpy. So enthalpy is nothing but energy, right? So enthalpy or energy. Now we have different kinds of energy. For example, enthalpy of formation, right? So formation enthalpy. Okay. Then bond dissociation enthalpy, combustion enthalpy, right? We have many kinds of enthalpy. So first we are going to be learning about standard enthalpy of formation. So standard means you have to mention, right? So here this is coming under the definition of energetics, right? So you should be able to write down the definition of each enthalpy types. So when we ask the definition of standard, then you have to mention that 1 mole of the substance is formed, right? 1 mole of the substance is formed. So you have to mention the amount as 1 mole for standard, right? Okay, so formation, for example, let's say from carbon and oxygen, right? From carbon and oxygen, CO2 is formed, right? So CO2 is formed. Now CO2 exists as gaseous state, right? And carbon, in which state carbon exists?
Oh wait, sorry, my thing had been muted.
Yeah,
Carbon
in
what,
which-
sorry?
Carbon solid state, right?
Yeah.
Okay. Then again, oxygen in gaseous state. Now you see here we have, if you balance the equation, then you will have 1 mole, right? So in order to form 1 mole of carbon dioxide, we have to form it from the naturally occurring stable elements, and during this process we will have some amount of energy. That energy is called delta H theta formation. We have to denote it using this notation, delta H theta F. Okay, now you can just read this definition. The enthalpy of formation of elements in their most stable form. Why do we say most stable form? Because carbon dioxide can exist in solid state also, but naturally it will occur in gaseous state, right? So it will be formed in the most stable form. Okay, have the standard enthalpy of formation of, okay, that is not the definition. Okay, now here you see for carbon dioxide, we require carbon and oxygen from its naturally occurring stable form, right? So now we have the several forms of allotropes for carbon, right? For example, graphite. Can you just tell me the allotropes of carbons?
You have C12.
I'm sorry?
Wait. I'm just trying to recall.
Okay.
You have lead?
No. So we have the allotropes
Oh wait, lead's
of
a
carbon.
different thing, right? Yeah.
Diamond, right?
Yeah.
Diamond. Fullerene. Did you study these things?
No.
Okay.
I
So
think
these,
that's next year.
okay. So these are called allotropes of carbons, right? So for graphite only, the delta H formation is 0, right? Now you see, in order to calculate the amount of energy released during this process, we have to take an assumption. The assumption is this. This is actually an assumption, okay? This is
Okay.
an assumption. So what we take is, now for the most stable elements, right? So stable elements have the delta H formation of 0. So for carbon, for oxygen, for let's say nitrogen, and what else, for sodium, for these kind of stable elements, we will say delta HF theta is equal to 0. This is an assumption, right? So if we don't take this assumption, we cannot find the standard enthalpy formation of molecules, right? So this is an assumption that we are going to take. The assumption is for the formation of element, right? So elements, they are
Yeah.
naturally occurring, right? They are not formed, right? That's why we
Yeah.
are taking the formation energy is 0. They are naturally occurring, right? So for example,
Yeah.
forming nitrogen gas from nitrogen atoms is the most stable form of nitrogen. So for this process, delta HF theta is 0. Okay, right?
Okay.
And when we define the standard enthalpy of formation, we will say, how can we define it? Should I write it down, or I don't know if they have given anywhere. Let's check. Okay, they have not given. Okay, so if you want to write down the definition of delta HF theta, you have to mention that the substance is the amount of substance formed is 1 mole, and they are being formed from the naturally occurring stable elements, and the amount of energy released or released or absorbed during this process is called what? Delta HF theta, standard formation enthalpy. Should I write this down here?
Okay.
Okay, so if you want to write down the definition, you can write like this. Definition: under standard conditions, in order to form uh, 1 mole of, you can write this way, 1 mole of substances from its naturally occurring elements under standard conditions in order to form elements, we or otherwise the amount of energy happening, this is just write down, you have to just write down in sentence format. How can you write this down? So I have mentioned all the things that you have to include in your definition, right? So what is the first thing?
Yeah.
You have to mention that
There
the
has to be
process happens at standard conditions. Standard
standard
condition means
condition.
the temperature should be at room temperature and the pressure should be 1 atm, right? And you have to
Yeah.
form 1 mole of any substance, and you have to form them from the naturally occurring elements. And during this process, the amount of energy happening during this process is called what? Standard formation of enthalpy, right? So you can write down, how can you can you just write down the like the definition in sentence format here?
Okay. The amount of energy required to form a mole of a substance from its naturally occurring elements under standard conditions.
Okay, that's fine. So when you are asked to write down the definition, you can write down in your own words, right? So if you want
Yeah.
to extend this, occurring elements, we will require energy. We will require energy. That amount of energy is called delta HF theta. Okay, so likewise you can define. Okay, right.
Okay.
Now here this is the equation using the standard enthalpy of formation values we for each reactant and product. Now for products we have to find out the, now you see during a reaction, right? So we will have reactants and products, right? So when a reaction happens, an amount of energy will be either released or absorbed, right? So that can be determined using the summation and the difference of summation of enthalpy change of products and reactants respectively. So what I mean is, now if you want to find out, let's say, let me erase all these stuff. Okay, so let's assume okay, we will just take the reaction that we discussed in the question, right? So A plus B gives you C. Okay, now we have to find out the delta H for this reaction, right? Now for this C we will have delta HF theta for C, delta HF theta for C. Now for this also we will have delta HF theta B, and for this also we will have a value, right? But I am just denoting using symbols, but for this formation enthalpies we will have a definite value. So delta HF theta A, right? So these are called reactants and this is called product, right? So sometimes products also might have some combination of substances, right? So in that case what we are going to do is delta H is equal to summation. So you know this symbol summation. Are you familiar with this symbol?
Sigma, right?
In mathematics, summation?
Yeah.
Okay, summation.
Or sigma, right?
Yeah, sigma or summation. We have to just sum up the values coming within this symbol. So summation delta HF products, okay, minus summation delta HF reactants, right? So if they include the term standard, then you have to mention delta H theta. This theta represents what? Standard conditions. Standard condition means the temperature is room temperature, pressure is 1 atm. Okay, right. Now we will just look at an example here. You see this example. The reaction is a formation of ammonia from nitrogen and hydrogen gases, right? So now you know this is a molecule. Ammonia is a molecule. For that we will have some amount of formation of energy, right? So that value should be given. But the formation enthalpy of nitrogen gas and hydrogen gas will not be given, but you have to assume those values are zero because they are the naturally occurring stable elements, right?
Yeah.
Do you understand? So now nitrogen gas, you can read this one. Nitrogen gas and hydrogen gas are the most stable forms and have delta HF theta. Now here they have given, but in the question, if they give this equation and they have just given the formation enthalpy of ammonia, you cannot ask the formation enthalpy of nitrogen. Hydrogens are not given, so I cannot do this question. You can't think like that. So you should know the assumption, which is for the naturally occurring elements, the formation enthalpy is zero. Okay, so if we apply this equation here, so you can write this way: summation delta H. If I denote this as delta H is equal to summation of delta H formation ammonia minus summation of delta HF reactants. Now here we have two reactions, right? So now here if you write this down, delta HF, since we have only one product, this can be written as delta HF NH theta. I have just keep this symbol because I have only one, minus again delta HF N2 plus delta HF H2. Okay, theta. Theta. Now for this we have been given this value. Where is the value? here,
101.
right? So
Oh,
the standard enthalpy
yeah.
of formation of ammonia, you don't need to remember this value. This value will be given in the question, so you can just
Okay.
substitute this value minus then you see here you okay. Now there is another thing also, right? So now we have studied that the standard formation enthalpy is defined for only 1 mole, right? 1 mole. But how many moles of ammonia we have here?
You have uh you have 2.
2 moles, right? So for
Yeah.
forming, for in order to form 1 mole, so in order to form 1 mole of ammonia, this amount of energy is released. So if we want to form 2 moles of ammonia, then 2 times of this amount should be there, right? So we have to just multiply 2
Yeah.
times of minus 45.90, right? Then minus, this
Yeah.
minus is in the equation. Then again, for this we have 0, for this also we have 0. So definitely the answer would be what? Minus 91.8 kilojoule per mole. Okay, per mole. So which
Okay.
means here we can skip this mole minus 1. Okay, now if you see this one, here I have written mole minus 1, but here there is no mole minus 1. Why is that? Why is that? Can you understand the the difference I am telling? So I wrote mole
Because
minus 1
that's
here, but in the answer mole
yeah.
minus 1 is not mentioned. Because why? Because when you are
Because this is for
substituting the
2 moles
values,
anyway.
when you are substituting the values, you have to substitute along with the units, right? So now if I substitute, this is how I should have substituted, right? So 2 mole, because we have 2 mole, into minus 45.90 kilojoule mole minus 1, okay, minus 0 plus 0. Now this mole minus 1 and this mole will go, so the answer would be minus 91.8 kilojoule, right? Because this enthalpy is not defined for 1 mole, it is general value. Okay, this is general value.
Okay.
So we don't need to put mole minus 1. If you put mole minus 1, then it's wrong. Why is that? Because we are defining this amount of energy is released for mole minus 1, but we cannot tell because we have a collection of substances. So a collection of substances cannot be expressed in terms of mole, right?
Yeah.
Okay. Now we will look at the second example, right? So if you look at the second example, now this is a reaction, right? So methanol is burnt. What is happening here? This is methanol. Did you study organic chemistry?
No.
Okay. So the name of this, the organic substance is methanol, right? Are you familiar with this term, methanol?
I've heard it once or twice,
you have
but
heard about,
not
right?
that
So
familiar.
now methanol is burnt, right? Because if we are reacting something with oxygen, then it means we are burning, right? So during the process of burning an organic compound, we will end up with carbon dioxide and water. I think I have already discussed this in the third module, right? So if we burn any organic substance, then carbon dioxide and water will be resulted, right? Did we study that?
Yeah.
Okay. Now you see, if we apply this equation here, how you have to write this is delta H is equal to, now we have to just add the formation enthalpies of this products. So we have 2 moles of carbon dioxide, 2 moles of carbon dioxide, 2 times. Now in the chart they have given the delta H formation, right, in kilojoule mole minus 1. Why have they given the values in kilojoule mole minus 1?
Because it's per mole of the substance.
Yeah, because we have to define the delta HF per mole, right, for the formation of 1 mole. That's why. So for CO2, that is what? Minus 393.5. Minus 393.5. Then plus, again, how many moles of water we have?
You have
3.
3 moles of
3
water.
moles, right? So you can just put mole
Yeah.
also here, and here kilojoule, mole minus 1, here 3 mole, right? Into for water, that is minus 285.8. Then minus, this minus is in the equation that we studied, right? Again I have to put the summation enthalpies of reactants, right? So now you see oxygen here they have given, right? But even if they don't give this hint, you should know that is 0. Okay, sometimes in here
Okay.
they have given, but in A-level examination in Sri Lanka this value is not given, right? So even they don't even if they don't given, you should know for oxygen
It's
that is
0.
0. Okay, so now you have to
Okay.
just see this is 1, right? 1 mole, we have 1 mole into for the formation of ethanol we have this value minus 234.7 kilojoule, mole minus 1, mole minus 1. Now this mole and this mole minus 1, this mole and this mole minus 1, this mole all will cancel. So if you just simplify this, you will get this answer, right? So delta H is equal to minus 1879.1 kilojoule. So from the value of delta H, you can tell whether this reaction is exothermic or endothermic. Can you just tell me if it is exothermic or endothermic?
If it's negative, it is endothermic.
Why? Is it exothermic? No, no. And is it endothermic? It is exothermic because why? Exothermic because energy is released, right? Minus means
Ah,
energy
yes.
is released. So
It's
if the
released. Yeah.
delta H is minus, then we will say that is exothermic, and if delta H is positive, then we will say that is endothermic, right? So endothermic means
Yeah.
from the system, from the environment, the energy is absorbed, right? But here during this
Yeah.
process, right, when we burn the organic material, then energy will be released to the environment, right? And here for combustion reaction, it is important to remember that the standard enthalpy of combustion is defined as the energy released per mole of fuel completely combusted. Okay, now there will be a question.
Okay.
I will just try to give you. Can you just give me 1 minute? I think it was held in 2030. So until I take the question, you can just revise what we have studied so far.
Yeah.
I think for that question we have to study Hess's law also. Okay, now we will just go through the module and then we will come to the questions, right?
Okay.
I have sent some questions, and after, if we can try to do them today, but otherwise, we will do them in the next session, right? So now we will just go
Okay.
through the questions. Now another question is given, right? So this is like a neutralization reaction where we make maybe react as an acid and base, right? So this is called neutralization reaction, right? So during a neutralization
Mm.
reaction also energy will be released, so that will be an exothermic reaction, right? So by just looking
Yeah.
at the sign of the value, now here you see delta H here, now delta H value will have two components. One is the sign and the other one is value, right? The value. Now
Yeah.
the sign will tell you whether it's exothermic or endothermic, and the value will tell you how much of energy is released or absorbed, right? Okay. Now you
Uh-huh.
see sodium hydroxide aqueous, HCl aqueous, and when they both react, you will get NaCl aqueous and H2O liquid. Now you see now this chart will be given, right? So if this is an examination, first they will give the reaction, right? And then they will give this amount, this
Yeah.
type of chart, and this will not be given. You are supposed to write this. Okay. Now you see
Okay.
delta H, and since this is a physical chemistry part, you should be very careful about the physical states of the substances, right? Now delta
Yeah.
HF is given, and delta H solution, right? So what do you mean by delta H solution? Now we have already defined the formation enthalpy means in order to form 1 mole of substance how much energy is required, right? And then delta H sublimation, right? Let's say, what do you mean by sublimation?
The process of going from solid to a gas.
Solid to gas. Can you give me an example?
Dry ice.
I'm sorry.
Dry ice.
Dry ice. Okay. So now solution, right? So solution means we
Yeah.
have to take 1 mole of any substance, 1 mole of any substance, and we have to dissolve it in
Oh
water.
yeah.
So during that process,
No.
Okay, fine. So during this process, how much amount of energy will be released, right? So now you see
Mm.
sodium hydroxide is formed in solid form, right? So uh, from sodium, from oxygen, and from hydrogen, right? So this is how we had to write, right? So sodium solid plus oxygen solid plus hydrogen gas, I'm sorry, oxygen gas becomes NaOH, right? So now during this process, delta H theta is equal to what? Minus 425.953. Okay, minus
Mm.
425.93 kilojoule mole minus 1. Now if you are asked to write down the equation for the formation of sodium hydroxide, this is how you have to write, because why? By definition, sodium hydroxide should be formed from the naturally occurring stable elements, right? And again,
Okay. Yeah.
for HCl, how can you write that?
H2 plus
H2
CO2.
gas plus Cl2 gas becomes HCl.
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 Having 2 in front
Now
of
you
the
see,
HCl.
okay, now if you just look at the first reaction, this reaction, and after writing down each reaction, you have to check if the reaction is balanced or not, right? Now you see,
Yeah.
when you can you just try to balance this equation, the first one?
Put it the very first one,
Yeah, I'm asking to
the NaOH one, or
this one, first one.
okay. NaOH. No. 2. Okay, so 2 here and I have 2 in front of the Na.
Yes. So when you okay, 2. Okay. So conventionally, when we are balancing this equation, this is how we have to balance. But when we are writing the equation for the formation enthalpy, we have to make sure that the substance is formed of 1 mole, right? So the substance here formed is NaOH. So
1 more.
so it should be 1, right?
Use
So
half.
it should be 1.
Yeah.
If it is 1, then this also should be 1, and this should be half, and this also should be half. Okay. Then again, if you
Okay.
write this, I mean, like this is also wrong now, right? So it should be 1,
Yeah.
so it should be half, and it should be half, right? So definition is
Mm-hmm.
very important for the formation enthalpy. Now for sodium chloride, there is no, can you just write down, so for sodium chloride, how? Sodium plus Cl2 gas, but sodium is in solid state. Now it will become NaCl, right? So it should be 1
NaCl.
mole, so chlorine should be half mole. Okay.
Half.
Now we have produced sodium hydroxide in its solid state, right? But in the experiment, we
Yeah.
are using in aqueous format, which means we are dissolving it in water, right? So while dissolving sodium hydroxide in water, an amount of energy is released. This amount of energy is released. Again for HCl also, this amount of energy is released. But NaCl, right? So NaCl is also formed in solid state, right? NaCl is also formed in solid state, right? So that is basically domestic salt. But since we have water in the system, again it will dissolve and give you sodium chloride aqueous. For that also, this amount of energy is released or absorbed. Released
Which one?
or absorbed. Here 3.9, before that we have positive, so this amount of energy is absorbed, right? Here released,
Yeah.
and here
Okay.
also released. Okay, you should be very careful about the
Okay.
terms released and absorbed. Okay, but for
Okay.
H2O there is no dissociation, I mean the solution enthalpy, because it's in the aqueous form, right? So that's why they have give not applicable. Now you see, we have to find out the net delta H, right? So during the formation, this amount of energy is released. again this amount of energy is released. So totally we have to just add them, right? So this is the total energy, this is the total energy of NaOH aqueous formation. And for HCl also, now this amount of energy is released while forming HCl solid, HCl gas, okay, HCl gas. And again,
Okay.
when you dissolve it in water, this amount of energy is released. So the net energy will be this. You have to just sum, right? If you just now
Okay.
this is like this: -2, -3, -5. No.
Yeah.
Likewise, we have to just add them, right? So when you are using calculator, you have to be very careful. So since we have like symbols, we have to just add them, and negative will be the value. And if we have like this, for example, but for this case we have to subtract, right, the difference, because we have different signs, so we have to just subtract 411.12 and 3.9, but the negative will be the highest value, so minus 407.22, right? So you understood these 3 points?
Yeah.
Okay, now we have to just substitute this in the equation, right? So I will just create some space here, and okay, so if you just look at this, delta H is equal to NaCl plus H2O liquid, the summation of the formation enthalpy of the products. And again, minus is in the equation, and in the examination you better write down the the original equation also. Original equation in the sense, this equation, delta H is equal to summation delta H formation products minus summation delta H. For this they might allocate some marks, right? So before starting any question, you better write down and then substitute. Okay, so
Okay.
before this you should have written the original equation, and then NaCl plus H2O minus NaOH minus HCl. Now how many mole of NaCl we have? 1, right? So
We
1
have
times,
1, yeah.
and then we have to put this value, not this value. If you put this value, then your calculation will be wrong. This value, why? Because from the solid state, if we make aqueous solution, then this amount of energy will be absorbed from the system. So the net enthalpy will be this. So you have to substitute this. So 1 mole into this plus how many moles of water we have? This amount of water. So 1 mole into the formation of water is this, okay, minus 1 mole of
Okay.
NaOH this, and 1 mole of HCl this. Now if you substitute, this amount of energy will be released during a neutralization reaction. So neutralization reactions are the examples for exothermic reaction, right? So you should know some examples for exothermic and endothermic reaction, right? So from this you
Okay.
can tell the solution, the dissolving of NaCl is an endothermic reaction. You can just tell, right? For example, if you are asked to write down an example equation or example chemical reaction for endothermic reaction, then you can write this way: NaCl aqueous, NaCl solid becomes NaCl aqueous. So this is an endothermic reaction, because why? Energy is absorbed if the sign is positive. Okay,
Okay.
and then from this you can tell neutralization reactions are exothermic reaction. Okay,
Okay.
right. Now we will move to the average bond enthalpy. Average bond enthalpy means, now you see here, let's say there is a covalent bond, right? So normally
Yeah.
if we want to break ionic compounds, definitely you should give more amount of energy, right? Because it's like divorce. I have already given an analogy for ionic bonds, marriage. So if you want to break an ionic bond, you have to give very high amount of energy. But comparatively, for covalent bonds, you can give like average energy, right? It's like covalent bond, right? Now let's say we have a bond between A and B. right? So this is, let's say, a covalent bond. Now we have to split this bond and make its constituent elements A plus B, right? We have to just split this. Now if you want to break this bond, definitely we have to give energy, right? So if we are giving
Yeah.
energy, then for the system it's absorbing, right? So this will be a endothermic reaction again. Do you understand?
Mm-hmm.
Do you understand? So bond
Yeah.
breaking energies are endothermic reactions, right? So now for
Okay.
this also we have an equation, right? So when we break, for example, we have done the same example using formation enthalpy, right? For that we use this equation, delta H is equal to summation delta HF theta uh, products minus summation delta HF theta reactants. Now in terms of bond enthalpy, we can do this question, right? So if we want to make
Yeah.
NH3, then we have to, now you see N2 means it is like this, right? N2, here it's given, right? Now we have to split this nitrogen and the hydrogen. So after separating each individual molecules, then NH3, this nitrogen will combine with these 3 hydrogen atoms, and this nitrogen will combine with these 3 hydrogen atoms and produce 2 NH3. Do you understand? So in terms
Yeah.
of bond enthalpy also we can calculate the amount of energy happening during this reaction, right? For that we have this equation, right? So that we are going to study the second equation now, right? So now for delta H we are going to use this equation. This is nothing. In the earlier case we subtracted formation enthalpy of reactants from the products, but now we have to calculate the average bond enthalpy of the reactants and bonds. Then from the reactants we have to subtract the product. You should be very careful. If you write down the other way around, then you will get the answer correct, but the sign will be different. If you are supposed to get negative, then you will get positive, right? So you have to always subtract the reactant from the product. Okay? Reactant first and then product. Do you understand? Okay.
Reactant minus product. Okay.
Now we will just look at this example and check if we get the same energy again. Okay, so now you see here they have given the bonds broken in the reactants, right? So now in the reactants the bond should be broken, and then here then there should be a new bond should be formed between the atoms, right? Now nitrogen triple bond, average bond enthalpy, right? Average bond enthalpy means what? Here, okay, now for example average of 2, 3 means 2 plus 3 by 2, right? Now here we have 3 bonds between nitrogen atoms. For breaking this bond we require some amount of energy. For breaking this bond also we require some amount of energy. For breaking this bond also we require some amount of energy. Now let's say we have X, we need X amount of energy, right? We need X amount of energy for this X, for this X, for this X, right? Now X plus X plus X will give you the total energy, right? And then divide by 3 is the 945. Now, okay, so for breaking these three bonds we require this amount of energy. If we are asked to find out the energy required to break only one bond in the nitrogen triple bond, then this is how we have to write down, right? So now 3x is equal to 3 times 945, then x is equal to
945. Sorry, mine was muted.
I'm sorry, wait. Okay, so now you see 3x, right? So if it is okay, now we don't need to divide by 3, right? Okay, this is like this. Now okay, let's say for breaking this bond we require x, for breaking this we require x, for breaking this we require x, but for breaking the entire 3 bonds we require 345. So now what you have to do, x plus x plus x is equal to 945. So 3x is equal to 945. So x is equal to 945 divided by 3. What is the answer?
$315.
315, right?
15.
So for breaking each bond, for breaking this bond we require 315, for breaking this bond we require 315, right? But that is not the case here. We can just substitute these values with the mole, the coefficient of the reactants, right? Now hydrogen single covalent bond. Now for breaking this bond we require 436, right? Likewise, how many bonds we need to break? 1, 2, 3, right? So first we have to write this down. Summation of bonds in the reactant side, that is equal to, we have to break 1 mole of nitrogen. For breaking this bond we require 945 kilojoule per mole minus 1. Then for breaking this bond we require 436. For this 436, for this 436. So 3 times 436, right? If we have 7 bonds, then 7 times 346, right? So if you just simplify this, what do you get? You can use a calculator. plus 3 times 436, 2253, right? 2253 kilojoule mole minus no, kilojoule only. Why? Because this mole minus 1 and this mole will go. Okay.
Yeah.
Right. Again you see here, again after breaking the bonds in the reactants, again we have to join these 3 hydrogens with each nitrogen, right? So now nitrogen single covalent bond. Okay, now you see here, in order to break it we have to give 391. So you might ask why we have to subtract, right? So if we want to break it we have to give this amount of energy, but if we want to form it, then this amount of energy will be released, right? Do you understand?
Okay.
So okay, now for example, let's say A becomes B, right? So if this is the forward reaction, delta H is equal to, let's say, minus X. Then for the reverse reaction, delta H is equal to same X, but the sign will be positive, right? So likewise you see NH3, right? So we have ammonia. If ammonia wants to become NN3 hydrogen, then 396 amount of energy should be given, right? But if we want to form NH3 using nitrogen atoms and 3 hydrogen atoms, then this is backward reaction, then it will release minus 396, right? So that's why we are going to, I'm sorry?
Isn't it 391?
I didn't understand your question.
Isn't it 391, not 396?
I'm sorry, 391. Okay. So while you substitute the values, you have to be very careful. 391.
Yeah.
So now you see, we are just, okay, now this is what happening here, okay. Now you see, here we have nitrogen like this and hydrogen, right? So if we want to break, this amount of energy should be absorbed, right? This amount of energy should be absorbed. So 2253 amount of energy is there. Now we have already studied the law of conservation of energy, right? And again, during the formation of these bonds, again now you see how many bonds we make? 6, right? 6 times
Yeah.
6 times 391. What is 6 times 391?
Oh, 6 times 391.
2073. 2073. No, right. Now in the system, it has absorbed this amount of energy, right? So the system contains this amount of energy, and for the formation of these two ammonia molecules, this amount of energy is utilized. Why? For the formation, the system releases energy. So from this you have to subtract 2073. So the answer would be what?
So 180? Yeah, 180.
180. So did we calculate correctly?
The
2253.
2253 is correct. No, wait. 6 times 391 can't be 2073.
Okay.
It has
what
to
is the
end in
value
a
here?
6.
What is the value here?
6 times 391 is 117. What? Let me type that in again. 6 times 391. 6 times 391. 2346.
2346, right? So now
46, yeah.
2346. So it will give you, I think,
Minus
minus
93.
93, right? So now you understood, right? So now you see the system contains this amount of energy, it has absorbed, and then for the formation of ammonia, 2 ammonia mole, it has released this amount of energy. Then for the process, so entirely the net process releases 93 kilojoule energy, right? 93 kilojoule energy. So when you are writing the answer, this is how you have to write. So first you have to calculate the summation of the reactants, I mean the internal energy of the reactants which contains during the breaking of the bonds, and then again you have to find out the internal energy of product while forming the bonds, and then the difference will be the overall delta H. Understood?
Okay. Yeah.
Again the same question can be done. Okay, now we can compare, right? So in this method we obtain a minus 93 kilojoule, and earlier also
We got minus 93, yeah.
we got minus 93.
Yes.
Yeah, minus 91.8 kilojoule, right? But here 91 only. Why? Because we are using different methods now. So sometimes while calculating the
No, we got
energy,
minus 93.
I'm sorry?
Don't worry, it's okay, sorry. I was looking at the wrong thing.
Okay, so now in the second method we obtain only 91, but here we have obtained 91.8. Why is the deviation? There is a deviation in the answer, right? Because we are here using the formation enthalpy, and here we are using the bond breaking enthalpy. So in calculating or in measuring the energy, sometimes we might commit some errors, right? So errors are inevitable. Errors are inevitable. That's why there is a small deviation. Anyhow, both methods can be used. Okay?
Okay.
Right. Now, so using the data given, you have to just use the values, but there might be a deviation in the answer depending on the method you are using, because while measuring the values we might commit some errors. That's all. Okay? So you don't need to bother about it.
Okay.
So now again you see here methanol, oxygen, right? So methanol you can write in this way, right? So methanol means it's an organic compound. So organic compound means there is a direct bond between carbon and hydrogen. So this is how we have to sketch methanol. So we have to just calculate. Here we have how many carbon hydrogen bonds, how many carbon carbon bonds, how many carbon oxygen bonds, how many oxygen hydrogen bonds, right? So we have to first summarize
Mm.
this. Okay, so how many carbon hydrogen bonds here? 1, 2, 3,
2,
4,
3, 4,
5.
5.
5. How many carbon? And you have to
One.
like you have to just cut it off, then only you can correctly count, otherwise you may make mistake, right? So 1, then
Okay,
again carbon
that's it.
oxygen 1, then oxygen
It's
hydrogen
1.
is also 1. And how many oxygen
Mm-hmm.
oxygen bonds are there? Double bond, in terms of
1.
double bond 3, but single bond
So 6
6,
single
but they will
bonds.
give the average bond, I mean the carbon. If they give the like average bond enthalpy for double bond, you can use the value for 3, but if they give the single bond oxygen value, then you have to use 6, right? So we will just check
Okay.
this depending on the data given, right? So carbon
Yeah.
single bond, right? So now carbon
Mm-hmm.
so this will be like times 346. Then again, how many carbon hydrogen single bond? 414 times 414. Then carbon oxygen 358. Then oxygen hydrogen, this one, right?
463.
463. 463. Then you see oxygen double covalent bond is given. Double covalent bond mean now for breaking this bond we require 498. So you have to just use, there are 3 carbon, I mean the oxygen double bond. So 3
Yeah.
times 498. Now if you just you have to just multiply this and this, plus this and this, plus this and this, plus this and this, plus this and this. Can you just quickly calculate it using a calculator?
Okay. Can you scroll up a bit?
I'm sorry, what is the value?
Can you scroll?
Summation
Can you scroll up?
Okay, I'm sorry.
Yeah, sorry. So 3, 2, 3, 7. 4,731.
4
731.
4731
Yeah.
kilojoule. Okay. Then again we have to calculate the average bond enthalpy for the products, right? So now for that also they have given a data, right? So carbon oxygen double bond, right? So carbon oxygen double bond, how many carbon oxygen double bond we have here?
You have 4 double bonds.
4 times 804.
804.
Plus again oxygen hydrogen single bond. How many oxygen hydrogen single bond here we have?
You got 6.
So 6 times
463.
Can you just, so this is summation products. What is the answer?
5,994.
Repeat it again. 9,000,
No, 5,000.
5,000.
994.
Okay. Now the delta H is equal to summation reactant minus summation product. So the answer would be 4731 minus 5994. What would be the answer?
Minus 1263.
Minus 1262.
Minus 1263.
Yes. Minus
1263.
3. Okay, so now again this is the answer. Okay, so you can do in this way also. Then we will move to the Hess law, right? Okay, right. Now we have a law, right? So for example, we cannot always take a chemical reaction will happen only in one step, right? So there might be multiple steps involved in the reaction. Anyhow, even the reaction happens in multiple steps, the total enthalpy will remain constant. So that is what Hess told, right? So for example, let's say here this is the elementary reaction. As I told you, elementary reaction happens in one step, right? So let's say this is delta H. This is what we have to calculate. But this according to, now how can you make an elementary reaction happening in multiple ways? If you add catalyst, right? So if you add catalyst, then it will produce an alternative pathway, right? So from A first B comes, then from B C comes, then from C D comes. For each step we have delta H. So what Hess told, so Hess was a scientist, so he told like when a reaction happens in multiple steps, then the overall enthalpy will be remain constant. So irrespective of which pathway reaction takes or how many intermediate products. So what are the intermediate products produced here? B and C. Okay. The overall reaction enthalpy remains constant. Okay. Now here, so delta H is equal to delta H1 plus delta H2 plus delta H3. Now we will look at an example where carbon dioxide is formed, right? So carbon dioxide can be formed from carbon and oxygen, right? So the formation enthalpy is this, right? We have already calculated, but you don't need to remember these values. But if the reaction happens in two steps, right? So first let's say carbon reacts with half mole of oxygen and produce carbon monoxide, and then again carbon monoxide reacts with another half mole of oxygen to produce carbon dioxide, right? So now this is delta H1, right? So now we can write in this way also. Carbon plus O2 becomes carbon dioxide, right? So now let's say carbon monoxide is formed, then plus half O2 carbon monoxide is formed. So now you see 1 mole of carbon dioxide gas should be formed, right? So now you see this is the second step. I mean the first step reaction, step 1, and this is step 2, right? So in the step 1, carbon reacts with half mole of oxygen, right? So carbon reacts with half mole of oxygen to produce carbon monoxide. Again the produced carbon monoxide again reacts with half mole of oxygen to produce carbon dioxide, right? Now you see for this we require minus 110.5 kilojoule, and for this we require minus 283 kilojoule mole minus 1. We don't know this value, we have to just add them. Okay, we have to just add them. How can you add them? If you add minus 110 and 283, can you check you get this amount of energy?
Minus 393.5. Yeah.
Okay. Now let's say if we have 2, right? So now you have in each step we have to balance the equation, right? So if you look at this step, now we have 1 carbon, 1 oxygen here, 1 oxygen here, totally 2 oxygen, here also 2 oxygen. But in this step 1 mole of carbon monoxide is formed. Now let's say if we have 2, right? So suppose we have 2 here. So again we have to multiply this by 2, right? While we are doing questions, we may encounter this type of questions also, right? So if we have
Yeah.
the coefficient except 1 before the substance form, then we have to multiply the formation energy by that number, by the stoichiometry ratio, right? You know stoichiometry ratio?
Yeah.
Okay, right. Okay, so again right, so they have given, what is this? So photosynthesis and respiration are both vital reaction in living cells, right? So normally photosynthesis happen in green plants, right? Green
That's
plants, and
yeah.
respiration happens in cells, right? Okay, now
Mm.
this is the reaction for photosynthesis, right? So this is for photosynthesis. Now can you tell me whether photosynthesis exothermic or endothermic reaction?
It absorbs energy, so it would be endothermic.
Endothermic reaction. And the opposite of photosynthesis is called respiration. It usually happens in cells, right? So during the
Yeah.
respiration, energy is released and absorbed by the cells, right? So this is
Yeah.
definitely an exothermic reaction, right? So now um, right, now for photosynthesis and respiration, we have to calculate the delta H, right? For that, we should know the formation enthalpy of glucose, oxygen, carbon dioxide and water. Definitely for oxygen, that is 0, because the oxygen is the naturally occurring stable element, right? Then for
Yeah.
I mean, like oxygen, they have given this amount of energy, right? And in the chemical equation, we are using glucose aqueous, right? Glucose aqueous. Then solution enthalpy also should be given. So have you ever dissolved glucose in water?
Uh,
Have you ever dissolved glucose in water? You
no.
just take a glass of water, right? Then you put some glucose, and if you touch the glass, what would you feel?
I'm not sure.
Coolness, right? So you can just demonstrate it at your home. You just buy a
Okay.
glucose packet and you just take some amount of water and you just put and stir it, right? Then you can observe the
Mm.
coolness in the glass, right? So which means the energy is absorbed from the environment for the dissolving purpose, right? So in order to dissolve the glucose, the amount of the energy is absorbed from the environment. Okay, right. Now for the
Okay.
formation, definitely for formation enthalpy is a exothermic reaction, but this is endothermic reaction. So the net reaction enthalpy will be this, right? And formation of carbon dioxide is given, for H2 also given, right? So now we have to find out the enthalpy energy, I mean the enthalpy of photosynthesis and respiration. We have just used this equation, right? So now you see, first we have to find out the you see, right, CO2 plus C6H12O6 gives, I'm sorry, CO2 plus H2O gives C6H12O6 plus oxygen gas, right? So this is basically photosynthesis, right? Now this is these are products and these are reactants, right? Now we can first calculate the delta H formation of this carbon dioxide and H2O, right? So here we have 6, here also we have 6, and here also we have 6, right? Now you see, we have to just find out the value for this, not for this, for this, right? Okay. Now if this is in the photosynthesis process, these are reactants, but in respiration they are products, right? They are products. Vice versa. Do you understand? The vice versa. Now this reaction is for photosynthesis, but the same reaction, but the backward reaction is the respiration. So in the respiration,
Okay.
glucose and oxygens are the raw material. So we can say reactants. Do you understand? So that's why they have
Yeah.
tabulated the
One person. One.
okay. So they have tabulated the data. I'm sorry. So they have tabulated the data like this, right? So for photosynthesis, this component comes as the reactant formation enthalpy, and the same components comes as the product enthalpy in the respiration, right? But the value will not change. The value will not change, right? So the value will not change. So 6 times of CO2, 6 times of this value plus 6 times of this value gives you this value, right? So I'm not doing the calculation,
Yeah.
I'm just explaining. And again,
Yeah. Okay.
for the respiration, this part becomes the reactants, right? For the respiration, this part becomes the reactants. Again, we can calculate for oxygen, that is 0, so we can ignore that. And 1 mole, 1 times, we already calculate the formation enthalpy of glucose, including the solution enthalpy, right? Because glucose exists as solid form, right? And in the reactants, also in the process, usually it becomes solution, and then the process happens, right? So delta H is this. Now you see delta H. Now for the photosynthesis, this should be subtracted by this. So this should be written first and then this, right? And you have to substitute along with the sign. So minus into minus plus, right? So plus, so this will give you positive symbol, right? And again this minus this, and this is the value. And you see the same value for the two processes, but only the difference is sign, which means photosynthesis is an endothermic
Endothermic.
reaction, whereas respiration is an exothermic reaction.
Except
Okay. Right. Now we will move to the concept called entropy, right? So entropy, we have already studied enthalpy, right? So entropy and enthalpies are completely different terms. Okay. So what do you mean by enthalpy? Can you just revise what you studied?
enthalpy is related to the change in energy, I think.
Yeah,
So
enthalpy is the amount of energy released or absorbed during a reaction, right? So entropy means it is a disorder, right? Disorder of a system. We have already studied a system, right? So for example,
Yeah.
let's say we have a brick, right? So let's say there is a wall, right? So now the bricks are arranged in order, right? So now the entropy is denoted using the letter S, right? So S is less. Entropy means disorder. Disorder means randomness, right? Randomness. It's a negative thing, right? Now, if we have a pile of bricks, right? So let's say a pile of bricks mean, will that be uniform? No, right? It's a disorder. Disorder will be there. Now there is a uniformity here, but here there is a disorder, randomness, right? So here we will say
Yeah.
S is high. S is high. Okay, so if you want to define the term entropy, entropy is a quantity related to thermodynamics where it depicts the disorderness of a system, right? So this is just the definition you can write in your own words, but can you just repeat the definition of entropy in your own words? What you understood?
It is the it's the permutation or combination of the way something can be arranged, a substance.
Okay, so disorder, right? Disorder or randomness.
Yeah.
Okay. So you see this entropy is the measure of how many ways a chemical substance can be arranged. Crystalline structures in solids are highly organized, right? For example, if you take sodium chloride, right? So entropy will be high because why? It has ionic lattice, right? Ionic lattice, right?
Yeah.
So 6 Na6Cl, that story, right? So there is a uniformity in crystalline structures. So the entropy will be less in crystalline structures. And there are some states in which entropy increases. For example, let's say solid becomes liquid and liquid becomes gas. In this direction, entropy will increase. Entropy will increase, right? So for
Increase.
example, you know how particles are arranged in solid, right? So very uniformly, very uniformly. There is no space among the particles as well. Now if it becomes liquid, then what will happen? It's like this, right? So randomness or disorder. Again gas, when it becomes gas, then again high disorder, right? So from solid to liquid, the disorder or entropy will increase. Again from liquid to gas, entropy will increase, right? So
Increase.
the
Yeah.
notation or unit will be S, and I mean the notation, right, will be S, and unit will be joule, mole minus 1, Kelvin minus 1. Okay, and like we studied the equation for delta H, here also we have an equation delta S is equal to summation of S products minus summation of S reactants, right? So for each reactant and products, we will be given individual values for the reactants, I mean the entropy values. Then we have to sum up the products entropy and then reactants entropy, and then we have to find the difference, right? So there are many paragraphs, you can just read them, right? Now you see here they have given an example. Right, so ice cubes slowly melting, right? So what will happen, right?
Yeah.
So ice cubes,
Entropy
when ice
increases.
cubes melting, right, during that process, will the entropy increase or decrease?
Increase.
Increase. Why? Because ice cubes is solid from liquid, right? Okay. Here the entropy of substance shows a trend with range of physical properties, right? So as I told you, entropy increases with molar mass. Molar mass means what?
The mass of a mole of a element.
Mass of a mole of a substance, right? So if you increase the molar mass, the weight is increasing. If the amount of substance increases, then definitely there will be a randomness, right? It will increase. For example, let's say we have 2 bricks here. 2 bricks here. We can say this is arranged, or we can say there is no disorder. But let's say we have 5 bricks like this. Okay. Now we can definitely say there is a disorder, right? So when the mass, molar mass increases, entropy will increase, right? Okay. Now F2 gas, I2 gas are given, right? So definitely the molar mass of fluorine is lesser than the molar mass of iodine because it lies in group wise, right? So from top to bottom along the group, the molar mass will increase, right? So for larger molecules, the entropy will increase, and The second point, entropy increases with melting and vaporization. This is what we earlier discussed, right? Solid to liquid to gas, right?
Yeah.
So from this state, right? So H2O liquid, this is the entropy. The value is 70, but for H2O gas, 189. So the value has increased, right? The entropy increases when solid or liquid dissolves in water, right? So now you see, we have sodium chloride in solid, right? Sodium chloride, solid state. But if it dissolves, then what will happen? Disorder will come. Disorder, randomness. It can spread anywhere in the water. So the randomness will increase, right? So for sodium chloride, the randomness is 72 joule mole minus 1 per Kelvin minus 1. But sodium aqueous, again it's like solid to liquid, right? It's like solid to liquid, the entropy will increase. Again, diamond and now this is malleability, ductility, you know, malleability, ductility things.
Yeah.
Okay, so entropy is lower in hard brittle substances than in malleable. For example, can you just tell me a brittle substance? For example, sodium, right? Sodium is a brittle substance. For that,
Yeah.
that will be lower, entropy will lower. For malleable substances, for example, iron and now here they have given diamond and plumbum. For example, iron, for iron, plumbum, for these stuffs, the entropy will be higher, right? But you don't need to remember these values, right? Entropy increases with chemical complexity, right? So complexity means again disorder. Complexity means again
Okay.
disorder, right?
Disorder.
Disorder. So when disorder increases, entropy also will increase. This is the summary. Okay? Right.
Okay.
Now, entropy change in chemical reactions. Right, so this is what I told you, and using this equation, now I'm just skipping this part. You can just read this and understand. If you have any, if you didn't understand, you can ask me, okay, then later. This one, entropy change in chemical reaction. Should I explain this also?
Okay.
Okay, now I'm just skipping this. If we require this while doing question, we will just come again and see, right?
Okay, yeah.
Right, now delta S is equal to summation of S products, summation of S reactants, right? So now you see, for the substances they have given S, right? And you should remember the unit of this entropy. Now for nitrogen, this is 191.6, hydrogen 130.68. Again you can see, right? So the chemical complexity of nitrogen is higher than hydrogen. That's why this is 130 and this is 131. Okay, and for ammonia it's again it's again higher. Why? Because complexity of ammonia is higher than nitrogen, so it should be 192.77, right? So now we have to find out delta S, right? Again, what you have to do, delta S is equal to summation of S products minus summation of S
Products minus
reactants, right?
reactants.
So now you see here again you have to remember the mole, right? Per mole, right? Here 2 mole, right? So what you have to do, 2 times here the product is ammonia 192.77 minus, this minus is in the equation. Then again you have to consider the reactants where we have ammonia and hydrogen, but we have 1 mole of ammonia, I mean the nitrogen. 1 times for nitrogen the value is 191.6 plus 3 times. If you forget to put this 3, then again definitely the value will be different, right? So you should be very careful about the stoichiometric ratio of the substances while calculating the entropy and enthalpy, right?
Yeah, okay.
This is 130. I'm sorry, why isn't it writing? Can you hear me?
Yeah.
My mouse is not working. Okay, so can you just revise these stuffs what we have studied so far until I rectify this issue?
Okay.
So I don't know what's happening with my device. So let me finish the session with this and try the questions, and we will meet in the next class.
Okay.
Have you left the meeting? என்ன இந்த மவுஸ் வேலை இல்லை மவுஸ் ஸ்டக் ஆகிடுச்சு என்ன செய்கிறேன் மவுஸ் ஸ்டக்